Laramie Basin, Wyoming Territory, October 1879. While his neighbors prepared their cabins for winter in the traditional way, chinked logs, banked earth, shuttered windows, a Norwegian immigrant named Lars Vikström was doing something they'd never seen before. He was digging, not for a root cellar, not for a well. He was burying a pipe that led nowhere, a pipe that ended in the middle of his cabin floor, a pipe that, according to every experienced builder within 50 miles, would do absolutely nothing except fill his home with frozen air and dirt. They laughed at him openly, called it Vikström's folly, told him he'd freeze to death come January, and it would serve him right for ignoring common sense. What Lars Vikström understood about earth temperature and air movement would save his family's life that winter and transform how frontier cabins managed interior climate for the next 40 years. Before we reveal what happened, hit that like button and subscribe to this channel. We're uncovering lost survival wisdom that modern engineering is only now beginning to understand. Comment below and tell us, where are you watching from? Your location might determine whether this technique could work for you. Now, let's dig into what this Norwegian immigrant knew that his American neighbors had never considered. The ridicule started the moment Lars broke ground. It was October 14th, 1879, and the first hard frost had already killed the late squash. Every homesteader in the basin knew what was coming. Wyoming winters didn't negotiate. You prepared right, or you suffered. Sometimes you died. Lars Vikström had arrived just 2 years earlier, speaking broken English, carrying techniques from a homeland most of his neighbors had never seen. He'd built his cabin following local methods, horizontal logs, stone foundation, mud and moss chinking, but now he was deviating in a way that made no sense to anyone watching. He was digging a trench, for feet deep, sloping gently upward from a point 60 feet south of his cabin, running in a perfectly straight line toward his southern wall. Thomas Bradley, who'd built 17 cabins across 3 territories, stopped by on the 3rd day of digging. He watched Lars haul another basket of rocky Wyoming soil to the surface, then shook his head. "You planning to pipe water?" Bradley asked, though he already knew the answer. The creek was a quarter-mile west. "Air," Lars said simply, not looking up. Bradley laughed. "It wasn't cruel, just certain. Air comes through the door for free, son. You're wasting daylight." But Lars wasn't piping air into his cabin. He was piping it through something else first. Over the next week, while neighbors finished their winter preparations, Lars lined his trench with flat stones, creating a channel exactly 8 inches wide and 6 inches tall. Then he placed a series of hollow logs end to end, cottonwood sections he'd hollowed out with patient chisel work, each one fitted tightly to the next with pine pitch sealing the joints. The pipe ran from an opening 60 feet south of his cabin, angled slightly downward into the earth until it reached maximum depth, then gradually rose again until it emerged through the cabin's stone foundation, terminating at a simple register built into his floor 3 feet from the corner fireplace. Sarah Lindholm, whose husband had frozen to death the previous winter in a poorly chinked cabin, brought Lars coffee on the morning he sealed the final joint. She was genuinely worried. "Lars, honey, that pipe's going to bring nothing but cold air and frost right up through your floor. You got 2 babies. Please, seal it up before winter." Lars smiled, patient and unmoved. "The earth is not cold like the air, Mrs. Lindholm. 6 feet down, she is always warm. Always the same." Sarah didn't understand. Nobody did. In their minds, underground meant cold, damp, dangerous, the place you buried the dead and stored root vegetables because nothing living should go there. What they didn't know was that Lars came from a region where survival depended on understanding what the earth does with temperature, where builders had worked with ground thermal mass for centuries, not against it. By November 1st, Lars had backfilled the entire trench, tamped it solid, and disguised it so well that visitors couldn't see where it ran. All that remained visible was a small screened opening 60 feet south, protected by a simple wooden hood and the floor register inside, both of which his neighbors considered monuments to wasted effort. Thomas Bradley made a prediction that everyone remembered later. Come February, Vikström's going to be chinking that register hole with frozen mud and cursing Norwegian stubbornness. He was half right about the cursing, but it wouldn't be Lars doing it. The principal Lars Vikstrom was applying had a name, though he didn't know it: geothermal gradient stabilization. Below the frost line, that critical depth where seasonal temperature swings cease to penetrate, the Earth maintains a relatively constant temperature year-round. In Laramie Basin, at 4 to 6 feet deep, soil temperature held steady around 50 to 54 degrees Fahrenheit, regardless of whether the surface air was baking at 90 degrees in July or plunging to 20 below in January. Lars's pipe was a heat exchanger, using the Earth itself as a thermal battery. When winter air, dry, frigid, and oxygen-rich, entered the southern intake, it traveled through 60 feet of buried cottonwood pipe surrounded by soil that refused to freeze. The air couldn't help but exchange heat with the pipe walls. Cold air warmed. The Earth barely noticed, its massive thermal inertia absorbing the temperature differential without measurable change. By the time that air emerged through the floor register, it had been preconditioned to approximately 50 degrees, cold by comfort standards, but 40 to 60 degrees warmer than the outside air it replaced. More importantly, it arrived without the violent drafts that plagued conventional cabins, where fresh air entered through gaps and cracks at full exterior temperature, creating frigid currents that no fireplace could adequately counter. But explaining this to men who built by tradition and visual observation was like describing color to the blind. "You're telling me dirt makes air warm?" John Hutchins, the settlement's blacksmith, said this while examining the floor register in mid-November. "Lars, I respect your effort, but that's not how anything works." Lars tried. He brought Hutchins outside, had him feel the screened intake, cold air being pulled in by the cabin's natural draft. Then he had Hutchins place his hand over the interior register. Warmer. Noticeably warmer. "Trick of the fireplace," Hutchins concluded. "Heat's just coming back up through your floor." It wasn't. Lars had deliberately positioned the register away from the firebox's radiant zone. But Hutchins had made up his mind, and the physics didn't match his mental model of how the world worked. The resistance Lars faced wasn't stupidity. It was the invisible barrier of assumed knowledge. Every builder knew that bringing outside air into a cabin made it colder. That was observable fact, repeated 1,000 times. Doors opened, cold rushed in. Gaps in chinking meant frozen children huddled closer to failing fires. The idea that you could deliberately bring outside air in and have it arrive warmer defied common sense. It required accepting that something you couldn't see, Earth temperature 6 feet down, mattered more than something you could see and feel every single day. Thomas Bradley's dismissal was more technical, and therefore more damaging. He'd built enough cabins to consider himself an expert, and experts don't appreciate immigrants suggesting they've missed something fundamental. "I've built 17 cabins, Vikstrom. 17. Not one of them needed a buried pipe to stay warm. You know what they needed? Proper chinking, banked earth against the foundation, and a well-designed firebox that doesn't waste heat up the chimney. Your pipe's going to fill with condensation, freeze solid by December, and crack. Then you'll have a tunnel for mice and cold air both. Mark my words." Bradley's prediction seemed reasonable. After all, warm air meeting cold surfaces does create condensation. In a poorly designed system, that moisture would indeed freeze. But Lars had thought of that too. His pipe sloped, gently, deliberately, so that any condensation would drain back toward the outside intake, never pooling, never freezing in place. The cottonwood logs, slightly porous, would absorb minor moisture without structural failure. And the constant airflow, pulled by the cabin's draft, would prevent stagnant air from creating ice dams. None of this mattered to the court of public opinion. By late November, Vikstrom's buried pipe had become a punchline at the trading post. Even sympathetic neighbors, the ones who brought his family venison and helped with roof repairs, considered it a harmless eccentricity at best, dangerous foolishness at worst. Sarah Lindholm, still worried, asked her husband to talk sense into Lars. "Let him learn," her husband said, not unkindly. "Some lessons only winter can teach." Winter was coming, and it had a curriculum in mind. December arrived cold but manageable. Daytime temperatures held in the teens, nighttime Lows occasionally touched zero. Standard frontier winter. Fires burned, children slept under piled quilts, and Lars's buried pipe worked exactly as designed. Quietly, unremarkably, drawing pre-warmed air into the cabin while his neighbors burned through their first cords of split wood fighting drafts they couldn't see. Nobody noticed the difference yet. A few degrees of efficiency doesn't announce itself in mild cold. Then January came for them all. The storm system that meteorologists would later identify as originating from a rare Arctic outbreak began its descent on January 8, 1880. By January 10th, the temperature in Laramie Basin hadn't risen above zero in 48 hours. By January 12th, it had dropped to 18 below, and it stayed there. For 6 days, the basin experienced what frontier journals would call the frozen week, a sustained cold snap that killed livestock, froze wells solid, and tested every structural decision every homesteader had made. In conventional cabins, the battle was immediate and brutal. Fresh air, necessary for both breathing and fire combustion, entered through the only places it could, gaps and chinking cracks around door frames, the intentional ventilation gaps builders left near the roof peak. That air arrived at 18 below zero, creating invisible rivers of cold that sank to the floor, no matter how large the fire burned. Thomas Bradley's family huddled within 3 feet of their fireplace, wrapped in every blanket they owned. The far corners of the cabin, 10 feet from the firebox, registered temperatures in the low 30s. Condensation from cooking and breathing froze on the interior walls. His children slept in shifts, rotating proximity to the fire. He burned through 4 days' worth of wood in a single night, feeding the firebox every 45 minutes, and still his wife woke with frost on her hair. Sarah Lindholm's cabin, built by her late husband, had a structural weakness she'd never identified, a gap where the north wall met the roof line, invisible from inside, perfectly positioned to channel frigid air down the back wall. Her 2 children slept in the same bed with her, their combined body heat the only thing preventing dangerous cold exposure. She burned furniture on the 3rd night, a chair first, then a small table, because her woodpile was dangerously low and the temperature showed no signs of rising. Across the basin, the pattern repeated. Families burning excessive wood, sleeping in coats, surviving but not comfortable, counting hours until the cold broke. And then there was the Vikstrom cabin. Lars woke on the morning of January 13th, the 4th day of extreme cold, to a cabin temperature of 61 degrees Fahrenheit. His fire had burned down to coals overnight. His children slept uncovered in their bed. His wife was baking bread. The buried pipe was delivering air at approximately 50 degrees, pre-warmed by earth that refused to acknowledge the Arctic outbreak happening 6 feet above it. That air fed the fireplace, supported combustion, and replaced the cabin's atmosphere without creating the drafts that plagued every other structure in the basin. Lars's firebox consumed roughly half the wood of his neighbor's fires, yet maintained superior temperature stability because it wasn't fighting against rivers of 18 below air constantly infiltrating the structure. He didn't gloat, didn't venture out to tell anyone, just maintained his fire at a modest level and waited for the cold to break. But Thomas Bradley noticed. On the afternoon of January 14th, desperate to understand why his own firewood was disappearing at an alarming rate, Bradley walked the settlement, observing chimneys. Thick smoke from most cabins, fires burning hard, consuming wood fast. Then he looked at Vikstrom's chimney. Thin, steady smoke. A maintenance fire, not a survival fire. Bradley stood in 18 below cold, staring at that chimney, and felt the first crack form in his certainty. Something was different in that cabin, and the only variable was the thing he'd called useless. Thomas Bradley knocked on Lars Vikstrom's door on the evening of January 15th, 6 days into the freeze. He came humble, which was new for him. "Lars, I need to see your setup." Inside, the contrast was undeniable. Bradley had left the cabin where his breath fogged, visibly 6 feet from the fireplace. Here, the air felt like early October, cool but livable, comfortable. His cold-numbed fingers began to ache as they thawed. Lars showed him everything. The floor register, still pulling steady air. The fireplace, burning with a clean, efficient flame that indicated proper oxygen supply. The cabin corners, Bradley touched the walls, noticeably warmer than his own. "What's your inside temperature?" Bradley asked. Lars didn't have a thermometer, but his wife had been tracking it using a mercury thermometer borrowed from the trading post. "This morning, before I built up the fire, it was 58 degrees. Now, with the fire going moderate, it's holding at 64. Bradley did the math in his head. Outside temperature, -18. Inside temperature, +64. That was an 82-degree differential, maintained with what looked like half the wood consumption he was experiencing. "Show me the pipe again." They went outside, and Lars traced the buried line, explaining the depth, the length, the gentle slope. Bradley knelt at the intake, felt the air being pulled in. Cold, yes, but by the time it traveled 60 feet through earth that held at 50 degrees. The physics clicked. Finally, brutally, obviously. "Son of a bitch," Bradley said quietly. "You're using the ground as a warming tank." "Yes," Lars said simply. "The earth does not freeze so deep. She shares her warmth with the air that passes through." Bradley was experiencing something frontier builders rarely admitted: the discovery that their expertise had limits, and that those limits had just cost him 3 cords of wood and 6 nights of his family suffering. Over the next 2 days, as the freeze finally began to break, Bradley did something methodical. He tracked Lars's wood consumption against his own, measuring as precisely as frontier conditions allowed. The results were stark. Bradley's cabin: approximately 19 pieces of split wood per day to maintain marginal warmth, low 50s near the fire, 30s in far corners. Vikstrom's cabin: approximately 10 pieces of split wood per day to maintain consistent warmth, low 60s throughout. That was 47% less wood for superior results. But the real difference wasn't just efficiency, it was stability. Bradley's cabin temperature fluctuated wildly based on fire intensity and wind direction. Vikstrom's cabin held steady because the incoming air arrived preconditioned, its temperature divorced from surface weather conditions. Sarah Lindholm visited on January 17th, after the temperature finally climbed back above zero. She'd heard rumors, needed to see for herself. Lars let her place her hand over the floor register. Air flowing steadily upward, noticeably warmer than the room itself, which was already warmer than any cabin she'd been in all week. "Ow?" she asked simply. Lars explained it in his careful English. "The earth is a blanket, Mrs. Lindholm. Not for keeping warm in, for keeping the same. Deep down, she does not know it is winter. The air that travels through her warms before it arrives inside." Sarah started crying. Not from sadness, from a math she was doing in her head. The furniture she burned, the wood she didn't have for next winter, the solution she didn't know existed. "Could this work for my cabin?" she asked. Lars looked at her south-facing wall, mentally calculated the distance and slope required. "Yes, if the earth is not too rocky, if the distance is enough for the air to learn from the ground." By January 20th, 7 men had visited the Vikstrom cabin to examine the buried pipe system. By January 25th, Thomas Bradley had apologized, not with words, but by asking detailed questions about pipe diameter, slope ratio, and optimal burial depth. The useless pipe had just rewritten the rules of frontier heating efficiency. In winter, that patient teacher had provided the final exam that no amount of traditional expertise could have passed. If you're learning something valuable here, hit that like button and make sure you're subscribed. We're about to show you how this technique spread and why modern HVAC engineers are now rediscovering what a Norwegian immigrant proved in 1880. Drop a comment. Would this work where you live? By February 1880, the Laramie Basin settlement had split into 2 categories: those who'd seen the Vikstrom cabin during the freeze and those who'd only heard about it. The ones who'd seen it couldn't stop talking. Thomas Bradley became an unlikely evangelist. The man who'd publicly called the buried pipe Vikstrom's folly was now sketching diagrams in the dirt outside the trading post, explaining thermal mass and geothermal stability to anyone who'd listen. "It's not magic," he'd say, embarrassed by his earlier certainty. "It's just physics we weren't paying attention to. The ground don't freeze past a certain depth. Never has, never will. You run air through that stable zone. and it comes out warmer. Simple as that. But simple didn't mean easy. The first imitator was Jacob Morrison, whose cabin sat on a gentle, south-facing slope. Ideal terrain for a buried intake system. He started digging on February 8th, following Lars's specifications as closely as frontier conditions allowed. 60 feet of trench, 4 to 6 feet deep, sloped for drainage, lined with stone where possible. Morrison's soil was sandier than Lars's, which made digging easier but required more careful pipe sealing. He used hollowed pine logs instead of cottonwood, sealed with a mixture of pine pitch and rendered tallow. The work took him 11 days. When he fired up his system on February 20th, the results weren't quite as dramatic as Vikstrom's. Morrison's intake was 10 feet shorter due to a rock outcropping he couldn't excavate, but the improvement over his previous winter was undeniable. His cabin held at 58 degrees with roughly 60% of his normal wood consumption. Word spread beyond the immediate settlement. Sarah Lindholm, determined not to burn furniture through another winter, hired 2 men to dig her intake line in March, before the ground fully thawed and became muddy. Her cabin presented a challenge: heavy clay soil that required picks more than shovels, and a foundation that sat lower than ideal for proper register placement. They adapted, extended the intake to 75 feet to achieve proper depth, used kiln-fired clay pipe segments from the brickworks in Cheyenne, expensive but permanent and immune to rot. The installation cost her $22, a significant sum for a widow, but she'd calculated the wood savings would recover the expense in less than 3 winters. She was right. That following December, her children slept warm for the first time since their father's death. By late 1880, 11 cabins within 40 miles of Laramie had incorporated some version of Lars's buried intake system. The variations were fascinating. The Anderson family used a 60-foot copper pipe salvage from abandoned mining equipment, expensive but thermally superior to wood. Henrik Olofsson, another Norwegian, extended the concept by burying a secondary pipe for summer cooling, pulling air through the same stable earth zone to arrive cooler than surface temperature. A group of Swedish immigrants in the northern section of the basin pooled resources to dig a shared intake system serving 3 adjacent cabins, with individual registers controlling flow to each structure. Not every installation succeeded. 2 homesteaders tried to shortcut the depth requirement, burying pipes only 2 feet down. They got minimal benefit. The frost line in Wyoming reached 30 inches, so their pipes were still in the temperature variable zone. Another builder used unseasoned green wood for his pipe segments. They warped within a season, creating gaps that defeated the system's efficiency. But the successful installations shared common elements: adequate depth below the frost line, sufficient length to allow heat exchange, proper slope for drainage, and sealed joints to prevent air leakage. The trading post in Laramie began stocking hollow log sections specifically for air pipe construction. By 1882, it was common enough that newcomers to the territory were advised to dig your intake before you finish your walls. Thomas Bradley, to his credit, went further than adoption. He innovated. In spring of 1881, he designed a dual-purpose system that served as both air intake in winter and root cellar ventilation in summer. The same pipe that pre-warmed incoming air during cold months would pull cool, stable-temperature air across stored vegetables during warm months, extending their preservation time. His design added a simple valve system that could redirect the airflow into the cabin during winter, into the root cellar during summer. It worked beautifully, and by 1883, 17 cabins had incorporated his modification. Lars Vikstrom never charged a penny for explaining his system. He'd walk any homesteader through the principles, help them calculate the optimal pipe length for their specific soil and slope, even assist with the initial excavation if asked. When thanked, he'd wave it off. In Norway, we share what keeps us alive. Here should be the same. The buried intake technique spread beyond Wyoming. Trappers carried the knowledge into Montana. A Swedish family moving to Minnesota mentioned it in letters home, and suddenly Scandinavian immigrants across the northern plains were experimenting with earth-coupled air systems. By 1885, regional journals were publishing technical articles about the Vikstrom method or ground-coupled ventilation. Engineers began testing variations, measuring thermal transfer rates, documenting the precise relationship between pipe length, burial depth, and temperature gain. What had started as one man's useless project had become frontier standard practice, not through authority or mandate, but through the irrefutable argument of families sleeping warm while using half the firewood. The technique worked because it acknowledged a truth that traditional building had ignored. The earth, just a few feet down, exists in a different climate than the surface. Winter and summer are surface phenomena. Below the frost line, it's always autumn, mild, stable, willing to share that stability with anything that passes through. Lars had simply asked the earth for help and built a system that let the earth respond. The story of Lars Vikström's buried air pipe should have ended there. A successful frontier innovation, adopted and improved, eventually replaced by modern HVAC systems that rendered such manual solutions obsolete. Except it didn't quite work that way. By the 1920s, as electricity reached rural areas and coal furnaces gave way to oil and gas heating, the buried intake systems fell out of use. Why dig 60 feet of trench when you could install a furnace that required no earthwork at all? Convenience won, as it usually does. The knowledge didn't disappear entirely. It went dormant, kept alive in scattered journals, regional histories, and the memories of old-timers who'd lived through the transition. Then, in the 1970s, energy crisis hit. Fuel prices spiked. Engineers started looking for passive heating and cooling solutions that didn't depend on expensive, imported energy. And they discovered earth-coupled ventilation. They called it by new names: earth tubes, ground-coupled heat exchangers, geothermal ventilation systems. Patents were filed. Technical papers were published. The concept was treated as innovative, cutting-edge, a triumph of modern engineering thinking. The irony was noted by exactly nobody in the mainstream engineering community. They were rediscovering what Norwegian immigrants and indigenous peoples had understood for centuries. The Earth's stable temperature zone wasn't new science. It was forgotten practice. Modern systems improved on the frontier versions in meaningful ways. PVC and corrugated plastic pipe replaced hollowed logs, eliminating rot concerns. Mechanical ventilation fans replaced natural draft, allowing precise airflow control. Antimicrobial treatment prevented mold growth in the condensation-prone sections. But the fundamental principle, that air traveling through Earth below the frost line will equilibrate toward ground temperature, remained exactly what Lars Vikström had proven in 1880. Undeniable physics, waiting patiently for humans to pay attention. Today's sophisticated earth tube systems are installed in high-efficiency homes, LEED-certified buildings, and passive house designs. They're praised for reducing HVAC loads, improving air quality, and lowering carbon footprints. Some systems achieve remarkable performance: 12 degrees Celsius of temperature moderation year-round, 70% reduction in conventional heating and cooling loads, payback periods of 5 to 8 years. These are the same benefits Lars achieved with hand-dug trenches and hollowed cottonwood logs. The lesson here isn't about technology, it's about humility. When Thomas Bradley dismissed Lars's pipe as ignorant foolishness, he wasn't being cruel. He was being certain. Certain that his 17 cabins worth of experience had taught him everything relevant. Certain that traditional methods represented optimized solutions. Certain that an immigrant speaking broken English couldn't possibly understand something he'd missed. His certainty cost his family 6 nights of suffering and 3 cords of unnecessary firewood. The broader pattern repeats throughout history. Indigenous knowledge dismissed as primitive, immigrant techniques ignored as backward, traditional practices abandoned as superstitious, until crisis forces re-examination and modern engineers rediscover principles that were never actually lost, just disrespected. The Earth, 6 feet down, holds steady at 50 degrees whether you believe in it or not. Whether you're a frontier Norwegian in 1879 or a LEED-certified engineer in 2024, the physics don't change. Only the willingness to learn from it does. Lars Vikström died in 1904, 24 years after the frozen week that proved his system worked. His cabin, the original one with the buried intake, stood until 1937, when it was finally torn down to make room for a more modern structure with oil heat and electric lights. The new owners never installed an earth tube system. Why would they? They had thermostats now. Their heating bills that first winter were higher than Lars ever paid in firewood. The difference was they couldn't see the waste. It was hidden in monthly utility statements, not in depleted wood piles. Progress, measured in convenience, had moved backward when measured in efficiency. The story of the useless, buried pipe carries a simple moral. The next time someone from a different background, a different tradition, or a different way of thinking suggests something that contradicts your expertise, consider the possibility that your expertise has boundaries you haven't discovered yet. Lars's neighbors eventually learned this lesson. They learned it when their children shivered and their woodpiles shrank and their certainty collapsed under the weight of 18 below reality. We can learn it more gently, by listening first, measuring carefully, and remembering that wisdom doesn't expire just because the people carrying it speak unfamiliar languages or use hand tools instead of computers. The earth still holds steady at 50 degrees, 6 feet down. It's still willing to share that gift with anyone humble enough to dig a trench and patient enough to let physics work. All it requires is the willingness to believe that maybe, just maybe, the fool burying a pipe in October knows something worth learning. If this story changed how you think about traditional knowledge and modern innovation, hit that like button and subscribe. We're documenting forgotten frontier wisdom that's more relevant now than ever. Comment below. What traditional technique from your culture deserves a second look? We read every comment, and your stories might become our next video. The earth is still teaching. We just need to remember how to listen. This script presents historical techniques for educational and entertainment purposes. Any construction project involving earthwork, ventilation systems, or structural modifications should be designed by qualified professionals following current building codes and safety standards. Ground conditions, climate zones, and local regulations vary significantly. What worked in 1880 Wyoming may require substantial modification for modern applications.